All right, let's take a look at solving some word problems, and again, bringing everything together that we know in order to be able to address some of these word problems that can be really challenging for kids. So part of what we're going to be doing is bringing back the strip diagrams and any other diagrams that we have used, any visual representation, and now together with some of the more abstract symbolic manipulation, and see how much power we can actually get in solving these problems in a thoughtful, makes sense kind of way. So, problem number 1. At a store, a hat costs 3 times as much as a t-shirt. Together, the hat and t-shirt cost $35. How much does the t-shirt cost? So, the hat and the t-shirt, and we can clearly draw a strip diagram as is represented here, and we know that the total is 35. Right? So, we know, what we know from this diagram is that whatever this t-shirt costs, the hat costs 3 of those amounts, right? So whatever this is also the same amount. So when we're looking at 35, we actually have 4 pieces, 4 of those blocks is $35, right? We can see that from the diagram. So then one of those blocks is 35 divided by $4. Okay, so 32 divided by 4 is 8, so it's $8 and 3/4, so $8.75. So t-shirt costs $8.75. Right, so just from the visual, this is not high level symbolic manipulation. This is just visually making sense of the problem, and that's something that can be introduced fairly early on so that kids have time to make sense of the problem and have an opportunity to do that before they have to use much more complex and abstract techniques. However, if we want to say that if we want to use algebraic equations for this, we have a couple. So if we have the t-shirt is going to cost, let's say, $T, and hat is going to cost 3 times as much. So we could write it as 3 times T. We know that. And then we know that 2 of them together are 35. So T plus 3T equals 35. So 4T is 35. What times 4 is 35? Well, T is $8.75. So see how much more abstract the left solution is from the right. The right is focusing on the visual, making sense of what the numbers are, making sense of where the equation comes from. We should be able to see that this equation, T plus 3T, coming from this diagram, T for the blue square and the blue rectangle and 3 orange rectangles equals $35. So I would like you to see that although we probably had this strategy emphasized in our experience in our classrooms, that strategy can only be successful if it's built on some kind of basis in understanding and making sense of the problem. And strip diagram is an excellent way to do that. I'm going to leave number 2 to you to solve, but let's look at number 3. On a farm, 1/7 of the sheep are gray, 2/7 of the sheep are black, and the rest of the sheep are white. There are 36 sheep, white sheep. How many sheep in all are there on the farm? Okay, so we have a strip diagram. So this is going to be our first solution method so that we can make sense. So we have 1/7 of the sheep are gray. So this is the diagram that represents the 1/7 of the sheep. And how do we know there's 7? That this is a 7th? Well, we need 1, 2, 3, 4, 5, 6, 7 of them to fill the whole farm, to represent all of the sheep on the farm. Now 2 of those 7s are black. Okay, and the rest are white, which is 36. So I wonder how we can figure out how many sheep there are on the farm. Well, we know that this is 4/7. Can't we figure out what one of these is? 36 white sheep across 4 different little rectangles, right, should be 9. So we know that this is 9 sheep, right? It's visual. There's very little that we need to be doing here in terms of manipulation of symbols. We need to be looking at visual and making sense of it. And the question is, how many sheep are in the farm in all? Well, this is 1/7. So on the farm, there are 7 groups of 9 sheep. Okay. All right. So 63 sheep. Okay, good. So let's look at the algebraic way to do this. So we have 1/7 of the sheep are gray, 2/7 of the sheep are black, the rest are white. So 1/7 is gray, 2/7 is black, the rest are white. Now we can figure out if 1/7 is gray and 2/7 is black, so that means 3/7 are not white. So 4/7 should be white. And we know that 4/7 of the farm, the number of sheep on the farm, is 36. So if we're going to use our algorithms for this, we can multiply through by the reciprocal, right, if that's what we're doing. So then we have 36 times 7/4, which is 63 sheep. Okay, so again, notice that notice the difference in the feel of the left strategy and the right strategy. The left strategy cannot survive stably on its own without understanding the right strategy. So we have to give the students time and the kids time to make sense of the problems and draw them out. So I'm going to leave 4 and 5 for you, but let's take a look at 6. When a box of chocolates was full, it weighed 1.1 kilograms. After half of the chocolates were eaten, the box with the remaining chocolates weighed 0.7 kilograms. How much did the box weigh without the chocolates? So use the strip diagram and some equations as well. So let's do the strip diagram first. We have a box, and part of it is the actual box, and part of it is chocolates by weight. And together, this is 1.1 kilograms. Okay. When we eat half of the chocolates, right, so the box and half chocolates, we are left with 0.7 kilograms. So interesting. So how much is this? Oh, how much did we lose? We lost 0.4 kilograms. Do you see that the difference between those is 0.4 kilograms? So how much more do we have to lose to get to only have the box? So box is going to be 0.7 kilograms minus the rest of the chocolates, which is another half. The other half of the chocolates. So 0.3 kilograms is the box. Okay. So does that, visually it makes sense, right? Okay. Now let's see if we can do this algebraically. So box, let's call it B. And chocolates, oops, Let's call them C. And what are some of the things that we know? We know the box plus chocolates is 1.1. We know the box plus half the chocolates is 0.7. Right? Now, if you remember, we could either do systems of equations here, if you remember the systems of equations, or we can continue to figure this out more in terms of sense making. So if the box is 1.1 minus all the chocolates, right? But we also know that the box is 0.7 minus half of the chocolates. So if the box is both of those things, we can set it up on as an equation. So we have 0.4 equals half the chocolates. Okay, so 0.8 is the chocolates, and if the box plus the chocolate is 1.1 and the chocolates are 0.8, then the box is 0.3. Notice how much more difficult the use of algebraic process is for this particular example. Kids can figure out this example on their own in a visual way. The algebraic requires a lot more rigor and a lot more sophistication in order to be able to figure out. There's power behind the algebra, and the reason that there's power behind the algebra is when we're ready to create algorithms like this, then we're creating extremely powerful algorithms that we can use in many different ways. We can use them to make predictions and extrapolations. We can do a lot of stuff with algebra. We can fine-tune them, but that's at the expense of simplicity. And what we need to do is we need to make sure that we have the sense-making with the visual approaches and with the sense-making approaches before we take out the big, powerful tools of algebra. Okay. Now let's try number 9. I'll leave 7 and 8 for you. Let's try number 9. 10% more girls than boys at the party. Altogether, 168 children were at the party. How many boys were at the party? How many girls were at the party? Solve the problem in 2 ways. All right, so I'm going to grab this one and give us a little bit more space. Okay. There were 10% more girls at the party than boys. So let's see if we can draw a strip diagram. So if this is boys, the girls would be that plus 10%. Right? This is the 10%. This is the 100%. This is the 100%. If together there were 168 children at the party, how many boys were there? Well, if we want to break this up and make this visual, we could say that in total, whatever this group is, that there are more extra girls, how many of those blocks are there in the whole picture? Well, if that's 10%, then there would be 10 of them here, right? And the same 10 of them here. 10 of them here. So wouldn't there be 21 of those equals 168? 21 of these boxes equals 168 kids. Right. So a box is 8 kids. So how many boys are at the party and how many girls were at the party? Well, we had 10 of the blocks of boys. So 80 boys and 11 blocks of girls. 88 girls. Okay. Now let's take a look at an algebraic way of doing this. So if number of boys is B, right? Number of girls is 1.1B because we have 10% more. B plus 1.1B is 168. So 2.1B is 168. And if we divide to find B, we get B equals 80. So there are 80 boys and girls is 88. Okay. The thinking is there. The visual diagram is underneath the algebraic reasoning. Now, we need the kids to understand what's going on visually before they're able to consistently and reliably and effectively use the algebraic reasoning. Now let's take a look at the last one, number 11. And let's see, I'm going to clip that as well. Oh. Okay, Quint had 4 times as many math problems to do as Augustine. After Quint did 20 problems and Augustine did 2, they each had the same number of math problems left to do. How many math problems did Quint have to do at first? So let's make sense of how of these diagrams. So before, oops, this is the before. Quint had 4 times as many math problems as Augustine. Makes sense that this is Augustine, and Quint has 4 times as many of those blocks. After Quint did 20 problems, and Augustine did 2. Okay, so you see what's happening here. Quint did 20 problems, and Augustine did 2. They each had the same number of problems to do. How many problems did Quint have? That's very interesting. So what do we know here? We know that whatever Quint had, if this is Augustine, this is Quint. It's 4 Augustines, right? And he did 20 problems. Interesting. Minus 20. So this is what's happening right now is I'm being drawn into the algebraic, but I actually am stopping myself now because I think we should try and think like a kid. So let's see. 2. So this is 2. We know this is 2 because it's the same as Augustine. Then what's this? So the total was 20, so this is 18, right? So Quint did 18, and then the 2 that Augustine did as well. And now they have the same. So that's really interesting because we now know that this is 18. So our Augustine's amount is 3 blocks, which is 18. So 3 times Augustine's amount is 18. So Augustine's amount is 6. So that's 6 problems. So now we can answer any questions that we want. So Quint had initially, if each of the squares is 6, 24 problems. Augustine had 6 problems. Right? And we can check that that works the same way. That's a really interesting problem because the diagram itself is very helpful. And one of the challenges here would be to make sure that the kids are equipped enough to draw that diagram out before working out the problem. So let's look at the algebraic. All right. So Augustine, let's say he has 8 problems, and Quint has 4A problems, right? This is at the before. Now after, they're calling it after, not now, so after, whatever Augustine has left is the same as whatever Quint has left. So what Augustine has left is 2 fewer. And what Quint has left is 20 fewer. And that's the same. So this is one of the, at this point, we can look at the equation, right, and see if we can solve the equation. So let's see. So if we have an A on the left and 4 A's on the right. So if we, so A minus 2 and 4A minus 20. So we can do a couple of things. We can say A is on both sides. So we can look at balancing, and that the fact that that the balance is going to remain the same if we remove one of the A's from both of the sides, right, with everything else remaining. Now, and negative 2 is what minus 3A, what is 3A minus 20 is what minus 20. Well, if we want to subtract 20 and get negative 2, whatever that was is going to have to be 18, because 18 minus 20 is negative 2. So 3 times what is 18, and that's 6. Okay. So we again see, this is another example of where the visual representation can be solved a lot more naturally and based on sense making than the algebraic. The algebraic is very powerful, but it has to be based on the visual sense making of the problem.